if there is anything between similarity between him and I this morning, it will be that it's also my first time attending the PWC, even though I've been in Tuskegee for a few years. And so this morning, the information I'm going to be sharing with you is titled Morphological Features of Mixed Cover Crop Biochar Produced at 3 different pyrolysis temperatures. And so again, my name is David Ban, and I work with Dr. Pamleku here and Mohammed. So, all right.
The pointer has an advancer.
Oh, okay. Great, thank you. We only missed the laser. So biochar is a black carbon material produced from biomass sources. And the discussion has already started, which makes my work a little easier because some of the information is already out there. But when we talk about biomass sources, we are talking about any kind of biomass, wood chip, plant residues, manure, or other agricultural waste products, okay? And when you take that through a process called pyrolysis, then you come out with a black material similar to charcoal, which we call biochar. The purpose of transforming the biomass into the biochar, there's 2 purposes. The first one is carbon sequestration, and in fact, there's a lot of work going on around the country and even worldwide in terms of carbon sequestration. And the second one, which is the thrust of my talk today, is soil supplementation or soil amendment. And so talking about carbon sequestration, in fact, even in the United States right now, the companies are being asked to scrub their effluent gas, okay, so that they can capture carbon dioxide that is produced in their effluent gases and store it underground. And that's part of the effort towards addressing global warming as a result of carbon dioxide emission into the atmosphere. So the International Biochar Initiative, this is an organization based in the United States. They define biochar as a solid material produced from thermochemical conversion of biomass in an oxygen-limited environment. So I am a chemist by training, and so chemistry, chemical engineering, so I'll be saying a lot of terms that are chemistry related, so please feel free or take note of those and then ask me questions as I head towards the end. So I spoke about pyrolysis earlier, but pyrolysis is nothing but heating the biomass in the limited oxygen. If you have a lot of oxygen, then you burn it into ash and carbon dioxide. So you want to restrict the amount of oxygen that is present. And if you look at the picture, unfortunately, we don't have the laser pointer, but I'll be getting close to the screen to draw your attention to some things. So if you have a biomass and then you put it in a pyrolysis furnace. So this is a furnace system where you can put in the biomass, heat it to about to temperatures above 300 degrees Celsius in limited oxygen supply, and then you will produce basically 3 things. The first is the biochar, which is what we are interested in. The second is bio-oil, and then of course you also make some syngas. So the picture here just shows you how the biomass is transformed into biochar. Okay, so there are 2 main processes, the pyrolysis processes that is used to make biochar. There's what we call the slow pyrolysis, and then there is fast pyrolysis. So slow pyrolysis basically is temperature dependent. So you are talking about temperatures between 300 and 700 degrees Celsius. And then when you go into the fast pyrolysis, then you are looking at temperatures in excess of 600 degrees Celsius, even to the thousands. The heating rate is also very important when it comes to the slow pyrolysis. The heating rate, the material is heated very slowly and controlled. So you have the rate from 0.1 degrees, heating rate under 10 degrees per minute, okay? And then when it comes to fast pyrolysis, you can go even in the thousands. It's a very fast heating rate system. The key between the slow pyrolysis and the fast pyrolysis is that the target product for the slow pyrolysis is a biochar, whereas the fast pyrolysis, the target product is a bio-oil. So if you are interested in making biochar, then you have to make sure that your heating rate, all the parameters that goes with the slow pyrolysis, especially the heating rate, the heating temperature, you pay attention to those. And then, of course, if you are interested in the bio oil, then you can go for the fast pyrolysis. There are advantages and disadvantages for both the slow and the fast pyrolysis. So one advantage for the slow pyrolysis is that it has the highest yield of biochar, okay, and it can accept a wide range of particle size. As you transform the biomass into biochar, particle size is affected. I'll show you some images, some detailed images about the product, so you will understand what we mean by the particle size. And then when it comes to the fast pyrolysis, then you have a higher yield of bio oil. Okay. Of course, the disadvantages will be that for the slow pyrolysis, you have to have you need a further treatment of gases due to carbon monoxide, the presence of carbon monoxide in the gaseous product. But again, the focus is the biochar and not the gas. But if you are interested in the gas, then you might as well go for the fast pyrolysis. So I spoke about the concept of biochar earlier, and I said that there are two trace areas that are used for which biochar is being applied. And the first one I said is carbon sequestration. Carbon sequestration is towards environmental reduction of carbon dioxide in the atmosphere. And so this picture that I show you has a lot of information in it. I'm going to try to unpack it so the information that is in it can be carried. Now, it is a model that adopts like a simple industrial process where you have input and then the process and output. So you put in something in a process, and then out of the process comes the output. So right to your left side, right here, is your input, okay? The process is a pyrolysis, and the output is everything that is coming out of the pyrolysis process and its and the application. So you can think about this as your input. You can think about it as photosynthesis capturing carbon dioxide from the environment, okay? Photosynthesis capturing carbon dioxide from the environment to grow plants. And the plants can be anything, okay? It can be rice, sugarcane, and everything all the way to forestry, trees. And if we can capture all of this and carry it through a pyrolysis process and transform it into a biochar, the end result is that ultimately, some carbon dioxide has been taken out of the atmosphere. If you look at the width of the arrow, the red arrow going down, and the width of the carbon dioxide red arrow going up, giving you an indication of how much carbon dioxide has been sequestered by carrying it through the pyrolysis and everything that goes on here. It's almost like a half of carbon dioxide returning into the atmosphere, carbon in terms of carbon dioxide returning into the atmosphere for this type of application. So once you go through the pyrolysis and you make a biochar, the biochar goes into the soil. That's a huge sink for carbon, okay? The biochar contributes to soil amendment. Biochar is not a fertilizer, and I'm going to explain that further. It's not a fertilizer. It only enhances the soil properties. I will talk about those properties in the next few slides. But we have the carbon sink in biochar, and then we also avoid transforming the biomass into biochar. One of the properties of biochar is that microorganism activity in the soil resulting in emission of carbon dioxide, if it was just the raw biomass, is cut down. The carbon dioxide is cut down. Biochar is recalcitrant, which means that it's very, very stable in the soil. Microorganism is not able to degrade it into carbon dioxide. And that's one advantage. So the emission of methane and nitrogen, the nitrogen oxide is limited, and all of that fit into the reduced carbon dioxide that goes back into the atmosphere. So this is a huge part of the biochar initiative that is helping to remove carbon from the atmosphere, and for that matter, addressing climate change issues. But We are more interested in the soil amendment part. And where did all of this come from? All of this came from the Amazon basin, where soil referred to as terra preta has been identified by researchers as very good for plant growth. And that soil has some characteristics. It looks like charcoal. Some huge deposit of charcoal has been, injected into the soil. And this black material in the soil, as you can see on the right side of the picture, is facilitating plant growth. So what if we can transform biomass into biochar and apply it to the soil? How much are we going to be able to enhance the soil properties, to get us better yield and productivity? And that's where this talk is going. So, as I said earlier, biochar is not a fertilizer. It only helps the soil by helping the soil to retain water. So it helps the soil. It has a higher water retention property. It helps the soil with the soil structure. It enhances nutrient availability because the biochar absorbs nutrients from the soil so that the nutrients don't wash away or run off. It also has some cation exchange property. These are all research data. There's research data that has given us this information. On the extreme right is just the structure of biochar. So when you take a plant material, on the top is sugarcane bagasse that has been burned through pyrolysis. This work was done in Tuskegee University. And as you can see, the bottom is just a pine straw burned, transformed into biochar. This biochar has this spongy characteristic, which enables it to soak the water, and that's why it has increased water retention properties. So all of this is what actually is driving the addition of biochar into the addition of biochar to soil as an enhancement. We have, this guy, Lehman, and his colleagues also gave us an idea, because when it comes to biochar, at what temperature, do you just heat the temperature? Do you just heat the biochar to any temperature and then you try to and make the product? But we have a blueprint that guides us, and that came out of the work done by Lehman some time ago. And they told us that, well, if you have biochar in this green area, that's like a sweet spot for temperature between 400 and 600, somewhere 500. That's like a sweet spot where when you heat your biomass, then you can affect the pH. You have an optimized pH, all the parameters for biochar that are good for the properties that we saw in the previous slide, like carbon recovery, the surface area, cation exchange capacity, pH, and so on and so forth. You have an improved, so that's a great guide in terms of pyrolysis temperature. So why did we choose cover crops? Sorry, I'll get to the cover crops, but the objective for the study now is we are using cover crops. The cover crops are listed here: buckwheat, black oats, winter barley, cereal, and so on and so forth. We carry it through the pyrolysis. We have 3 different pyrolysis temperatures based on the temperature, the graph that I showed you previously, 400, 500, and 600. We will characterize this with 2 equipment, electron microscopy and Fourier transform spectroscopy. So the question is, why cover crop? Cover crop because cover crop has some benefits, and the text is messed up here. Yeah. Cover crops has some benefits, okay? So what I highlighted in the red, the text that is highlighted in the red is the properties of cover crops that is directly related to this. If biochar is not a fertilizer, but we can use cover crops which support soil health or improve biodiversity and nutrient management and water management, then we could be harnessing the properties of cover crop to go in synergy with the properties of biochar to support plant growth. And that's why we use cover crop. I see Prof. K standing behind me, so I know I'm screwed on the time, but this is our